Next, we need to introduce the concept of a one-to-one function. So when we have a function, it's passed the vertical line test. Functions can also have another property, and that is being one-to-one. A function is said to be one-to-one if each x value has exactly one y value. So for example, if the function f of x is the square root of the square root of x, this is a one-to-one function. Each x has exactly one y value. G of x is x squared. Now this is still a function, right? It's a parabola. It would pass the vertical line test, but it's not one-to-one because -2 squared is 4 and 2 squared is 4. A function is one-to-one if every horizontal line intersects the graph at one point. So once I have a function and I've done the vertical line test, I can then check to see if it passes the horizontal line test, which tells me if it's one-to-one. So for example, this right here, this is some line, right? This passes the horizontal line test, so this is a function, and that is one-to-one. This parabola here, this looks like y is x plus 2, kind of. You know, this parabola right here, this equation is not the point. It does not pass the horizontal line test, so this is not one-to-one. So let's determine if these functions are one-to-one. These are the functions we looked at, I think in the video it'll be right before this one. Right here I have 1 going to 2, 4 graphs to 5, and -1 graphs to -2. So this is a function, and it is one-to-one. For G, I have -3 go to 5, -2 go to 5, -1 go to 4, and 0 go to 1. So this is a function, but it is not one-to-one. And last, H, this relation of -1 goes to 0, -2 goes to 2, and -2 goes to 1. This is not a function, and something that's not a function can't be one-to-one because one-to-one is a property of functions. I can prove that an equation is one-to-one if I show that f of a equals f of b leads to the exact same result. So let's say I have f of x is -4x plus 12. This means I have -4a plus 12 equals -4b plus 12. Subtract 12 from both sides. -4a is -4b. Divide by -4. A equals b. So this is a function, and it is one-to-one. For problem 2, I have f of x is the square root of 25 minus x squared. Let's solve that in blue and give myself a little more room. So I'm going to, again, prove that f of a equals f of b will take us to a equals b. That means it's one-to-one, right? There's only one possible x value for each y value. So I have the square root of 25 minus x squared equals the square root of 25 minus, that was supposed to be a, b squared. So in order to simplify these, first I need to square both sides because squares don't do square roots. I've got 25 minus a squared equals 25 minus b squared. Subtract 25. Negative a squared equals negative b squared. A squared equals b squared. The square root of both sides. I get plus or minus a equals plus or minus b. Wait, hold up. That is not the same as a equals b. Now, if we were to graph this function, let's do that. Let's go to Desmos and graph this function. If we were to graph this function, look at that. It's a function because it will definitely pass the vertical line test, but it is not a one-to-one function. It wouldn't pass the horizontal line test. Back to our PowerPoint. So for a one-to-one function, it can have an inverse. An inverse undoes that function. So if I have a function f inverse will contain all the opposite points. So if I have the point AB in my function, the inverse that would undo that would have the point BA. So here, these two relations, f and g, are inverses because I have the point -2, 2, and then in g I have the point 2, -2. And f of x, I have the ordered pair point coordinate -1, 1. And then in g I have 1, -1. So my domain and my range are changing places in the inverse. Is one way to think about it. I've got 0, 0. I've got 1 in the coordinate pair 1, 3. And then the coordinate pair 3, 1. So they're all switching places. Let f be a one-to-one function. If you have a one-to-one function, it's going to have an inverse. It has to be one-to-one. That's why we introduced that property. Then g is the inverse of our function if every time we take f composed with g, it equals x. And if I take g composed with f, it equals x for all x in their domain. So that's why we did a refresher right at the beginning of this chapter and at the beginning of chapter 9 and when we first discussed this, I believe back in chapter 5 or 4. Function composition, because it's continued with us through the entire course, right? So let's practice how to prove two functions are inverses using function composition and how to find the inverse of a function.